Today's lesson is on momentum. So imagine that it's supper time for your cat. You place his feeding dish on the smooth kitchen floor and call him. He runs to the dish as fast as he can, but alas, he hasn't taken my science class and he doesn't know about momentum. What happens? My cat, he slides right on by and smashes into the counter, or the cabinets, and then stumbles around a bit as if nothing happened and saunters his way to the food dish. Okay? He had momentum. He kept on going. Okay? The momentum on the object depends on the object's mass and the object's velocity. Okay? So it depends on the object's mass and velocity. The more momentum an object has, the harder it is to stop the object or change its direction. Okay, so the harder it is to stop it or change its direction. So a couple examples. A fat cat and a skinny cat are traveling the same velocity. Which has more momentum? Well, the fat cat, right? Okay, because he has more mass. Okay, it'd be harder to stop him or change direction. Two cats are equally fat, but one is traveling twice as fast. Which one has more momentum? The twice as fast one, because it has a higher velocity. Okay, the more the mass or the more velocity is going to lead to a bigger momentum. There isn't really a good definition of momentum. This is kind of the definition from the book. Momentum is a quantity defined as the product of the mass and velocity of an object. So the definition is basically just the formula. Okay? We abbreviate momentum with a P because of the Greek word impetus. Okay, so P, the lowercase p, equals m times v. So momentum equals mass times velocity. Mass will usually be in kilograms, velocity usually in meters per second. So momentum will be kilograms meters per second. Okay? There isn't a simplification for it, so that's going to be what it is. It could easily be gram meters per second also. It doesn't matter. Okay? Notice that it's different than a Newton, because a Newton was a kilogram meter per second squared. Okay? This doesn't have the squared, so we just leave it as kilogram meter per second. Will momentum have a direction? Yes. Okay? It has a direction because it has velocity in it, and velocity had a direction. So momentum has to have a direction too. Okay, so problem. What is the momentum of a 90 kilogram football player running with a velocity of 9 meters per second towards the end zone? Okay. So P equals m times v. Okay. We're looking for momentum, so P equals mass. What's the mass? 90 kilograms times the velocity of 9 meters per second, so times 9 meters per second. 90 times 9 is 810. Of course, you know now that you have to do significant digits, and both of those only have 1. So 810 will round to 800. And what's my unit label? Well, the 90 was in kilograms and meters per second. So kilogram meters per second towards the end zone. Okay? We have to have our direction. So towards end zone is what that says. Okay, circle it. Done. Okay? So momentum of 800 kilogram meters per second towards the end zone. Now, what if a 120 kilogram lineman tackles him head on? How fast would he have to be running to stop him? Okay, this is a little bit harder problem. Okay? So let me show you how you do it. Again, your formula is P equals m times v. This time, we know what momentum he needs to stop him, right? The first football player had a momentum of 800 kilogram meters per second toward the end zone. So now the other guy has to have that. So it's going to be 800 equals the mass, which was 120, times the velocity, okay, which is what we're looking, how fast would. So we're looking for the velocity. Divide both sides by 120. And the velocity turns out to be 6.7, which we're going to round to 7 meters per second. The opposite direction, so towards the other end zone. Notice that this guy only has to run 7 meters per second, while this guy was running 9 meters per second. How is that possible? How is it possible for a slower guy to stop the faster guy? Because, remember, momentum is a product of the velocity and the mass. Okay? This 120-pound mass is much bigger, so the guy can be going less. Okay? Think about the shopping cart that we talked about before with like inertia. Okay? If you're pushing a full shopping cart, it's hard to stop it or change its direction. Okay? A lot harder than an empty shopping cart. This is kind of what this is showing too. This big guy, okay, doesn't have to be going as fast to have the same momentum. Okay. Next part is the law of conservation of momentum. During a collision, the momentum of the objects before the collision has to be the same as the momentum of the objects after the collision. Okay. Some or all the momentum may be transferred between objects during the collision. Okay. So basically, at the end and the beginning, you're going to have the same amount of momentum. Now, that's a perfect world. Some will get lost in friction and all that kind of stuff. So, but in our examples, the momentum before the collision has to be the same as the momentum after the collision. Okay. So, for example, a pool cue ball hitting another ball sliding into the pocket. We're going to do an example of that, and also a Newton's cradle demo. And let me show you that right now. So let me stop this and go to our camera here. So I have my Newton's cradle set up. Now, according to the law of conservation of momentum, if I pull back one of these balls and release it, what's going to happen? Well, one should go up the other side. Okay? The momentum from this ball, when it hits, is transferred through all these other balls into the last ball, so it went up. Okay? So the momentum is transferred through. So what's going to happen if I take two balls and release them? Okay? Then two balls have to go up the other side. The momentum is transferred through. Momentum cannot be gained or lost. Now, again, it doesn't go on forever. You see now it's basically done. It doesn't go on forever. Because there is friction, you might hear the sound, and there's the heat generated when they hit. So some of that momentum actually is lost. What would happen if I would do 3? Then how many should go? All right, shouldn't it be 3 go, but there's only 2 left? We'll do that in class so you can see that. What if I take 1 from either side and let them go at the same time? What should happen? Okay, looks like they bounce off, but really the momentum from this one is being transferred through to this one. The momentum from this one is transferred through to this one. Okay, so they keep on doing it. What if I would do 2 and 2? Okay, then 2 up either side. What if I would do 3 and 2? Okay, then one of them has to switch. And we're going to play around with these in class so you really get that idea. Okay, so back to what we were working on here. Okay. So I said, remember Newton's third law? His law tells us that momentum has to be conserved because the reaction force is equal and opposite. Okay, think of the pool balls or think of that Newton's cradle again. Okay, it should be obvious that if I release one of those balls, the equal and opposite reaction will be one goes up the other side. Okay, so conservation of momentum is just the same as Newton's third law, which is why a lot of people kind of put them together. Okay, we're going to end with a few things about collisions. I'm also going to show you some demos in class. I'm going to show the Astro Blaster. We'll play with the Newton's cradle, and we'll do some other things in class. So during a collision, objects can stick together. The combined objects are considered one object. The masses are added. The velocity and the direction depends on the angle of the collision. Okay. This example we're going to do in class. Basically what we're going to do, though, I can show you, we're going to do kind of like we had before. I'm going to have an intersection for a road, and I'm going to have a little car and a big truck, and they're going to smash together. Okay? And we're going to figure out where they go. But we're actually going to do it a little bit better than we did it last time, because we're actually going to use the momentums. We're going to have a mass and a velocity of the car, and we're going to have a mass and a velocity of the truck, and then we're actually going to figure out where they land. Okay, where are they going to land? So we're going to do that one in class. The next one is when objects bounce off of each other, momentum is transferred. The objects will change velocities and momentum, but if you add up the various momentums, they're going to be same as before. So we're going to do an aster-blaster example. Also, in this example, we could do something like a pool table. So let's say there's my pool table. I have the pockets here, something like that. And let's say that I have a ball here, and my cue ball is here, and I want to send this ball into the corner pocket. Okay. I do my mass and velocity, and let's say I'm just going to make up a number here. Okay, I do my mass and velocity, and I shoot this at it with a momentum of 2 somethings. I don't know what they are. Pool balls aren't very heavy. Okay. It hits this one. That ball goes right to the corner pocket because I have great aim, and the cue ball bounces off in this direction. Okay. If the pool ball here picks up a momentum of 1, what does the momentum my cue ball have left as it rolls away? Well, it has 1, because 1 plus 1 is 2. They have to add up. Okay. Do the same thing with bowling pins, and we can do this. We'll probably do this in class. The video's a little shorter. Okay. But we can have all these bowling pins and have our big bowling ball and send it flying and have all these pins scatter in different directions. But if we add up the momentum of each of those pins, they will equal whatever the momentum of the bowling ball was before the collision. Okay. And that's momentum.